this mantle and how that leads to kind of finger channel-like structures that can happen due to reactive feedbacks. I've thought a lot about ductile flow in porous media. And so what I'm just showing here is a neat little tracer field that is following a localized portion of melt in a ductile matrix. And you could think of this as a porosity wave, and I'm going to go into those a lot more later in the talk today. And then down here in this corner is a snapshot from a simulation that's off in the ether of review right now. And in this manuscript, we're thinking about the concurrent accretion and partial melting of Mars's planetary interior. And this is just a tracer field to snapshot so you can see the mixing. And then here in this bottom corner is a snapshot of a box model I did of double diffusive convection. This is just a composition field. It's sort of a temperature composition buoyancy model. It's just a fun picture, and it's on my website where you can see a couple simulations of models I've done. So I'm just now starting to break into thinking about volcano physics, and I've thought a lot more about mantle dynamics and other such things. But I promise I'll do a good job today. This will be at least as fun as watching the debate last week, and probably more fun than watching the news. So moving forward, I'm going to do a little case study about long period oscillations measured at volcanoes. And there's no better place to do it than the famous eruption at Soufriere Hills volcano Montserrat, which famously erupted from 1995 to about 2013. And I assume you're all pretty familiar with this volcano. So I tried to dig out something that I thought maybe some of you didn't know. Now, the famous Beatles producer, George Martin, sometimes known as the Fifth Beatle, has a recording studio that is just falling apart on the island. And it was kind of put out of commission by Hurricane Hugo in 1989, but it hasn't ever been used again since that hurricane hit, and then the volcano went active. So it's actually worth noting that Jimmy Buffett's 1979 album Volcano was recorded at this studio. And moreover, it's actually named after Soufriere Hills. So the studio still is unusable. I still think that Jimmy Buffett is unlistenable. So this is a reason why maybe dad rock fans or a frat boy might find this island interesting. But I hazard that this is why you might find it interesting, and why I might find it interesting too, is the really remarkable eruption cyclicity that's been observed at Soufriere Hills volcano. And this has been observed on several different length scales, time scales rather, for eruption cycles. But I'm going to focus in on these eruption cycles that have been measured on the time scale of hours to days. So if you look at this time axis down here, this is really just a week in January 1997. And what I want to draw your attention to is the seismic signal up here on the top panel. There are these peaks of average seismic amplitude that go throughout time that have sort of average peaks of 8 to 10 hours, looking pretty regular. And then at the same time, coincidentally, or maybe not coincidentally, but coinciding in time, these tilt meters that were placed on the volcano are measuring inflation and deflation. So inflation with increasing seismic activity. And these cycles go together. And this is later in the same year, just monitoring over about a month-long period. So on this x-axis here, we have repose interval between Vulcanian explosions. And over here, we have the binned number of Vulcanian eruptions. And so over this period of time, there were about 74 explosions with an average periodicity of 10 hours. So this sort of repose time averaged in on, 10 hours or so. And these fluctuations went along with SO2 degassing, and the cycle peaks coincided with accelerated dome growth and these eruptions. So why the cyclicity on this hour-to-day time scale? The most commonly invoked model to explain this is a family of so-called stick-slip models, wherein a crystal-rich plug sits on top of a volcanic conduit at the edifice of the volcano. And compressible fluid can build up pressure behind this plug until some sort of threshold, some stress threshold is reached, and then the plug is pushed upwards, and the friction between the plug and the edifice causes the shaking that we see in the seismic signal, and that allows for there to be the release of the gas. So there's the depressurization and the deflation of the edifice. So that explanation has been readily used to explain the observations at Montserrat. More recently, Michaud and others proposed a alternative or complementary model wherein porosity waves are the mechanism that's responsible for the cycles of inflation and deflation, along with the coincident explosions and periods of elevated degassing. And so in this idea, in this conceptual model, sort of layers of increasing vesicularity periodically reach the top. Now, these porosity waves as a mechanism for fluid transport or gas transport arise naturally when you have percolative flow in ductile materials. And so what's interesting about this model that was put forth by Michaud and others is that when the fluid percolating through this semi-permeable magma is compressible, upon decompression, these layers of vesicularity can grow and localize dynamically. And so what they hypothesized was that there could be a characteristic length scale between layers of vesicularity that grow the fastest, and those layers would be governed by a distance that's set where gas expansion, so the decompressing gas expanding in the pore space, is able to balance the overburden in magma compaction. So this is a pretty good schematic scientific illustration if I want to kind of explain a little bit further what I'm going to mean by porosity waves moving forward. So I'm going to start with panel C here. The x-axis is gas fraction, and the z-axis or y-axis, I suppose, is the height in the conduit. Now, this smooth line in the background is a solution for a steady state gas fraction in this conduit. And then this overlain wiggly line is the departure from steady state. And so what's happened in this model is the authors have taken the gas fraction at the bottom boundary and they've shaken it randomly, causing a chaotic looking sort of porosity wave-like signature. But what you see is some smoothing, and as you go up the conduit, these gas waves decompress and sort of choose this periodic wavelength of vesicular high, which is denoted by these yellows. So this is excess gas fraction, and sort of gas deficits, which would be these low areas. So what's happening is gas expansion is finding a way to balance magma compaction, and that's selecting the distance between these high slugs of gas fraction and these low slugs of gas fraction. And this only works because the gas is decompressing. In the event of there being a not decompressible gas or a fluid, porosity waves tend to be conservative in shape. So these little wiggles would just travel up the conduit without really doing anything. And so I'll talk a little bit about amplitude of porosity waves. And when I say that for the purpose of this talk, I really just mean excess or deficit gas fraction. And when I talk about frequency, I really do mean 1 over the spatial wavelength of these waves. So, you know, peak to peak or trough to trough here. So the nice part about the model presented in the 2013 manuscript I've summarized for you is that the equations were simple enough to be linearized and do a dispersion analysis. And so this allows the authors to make some nice predictions based on their linear theory. And I'll sort of summarize the crux of it here is that in the limit of there being an incompressible gas, there's no expansion. And if there's no compaction, the gas wave growth is only governed by the decompression of the gas, so the compressibility of the gas. However, in between, there's this region that depends on the wavelength of the porosity wave, wherein you can find negative growth rates, so shrinking porosity waves for short wavelength areas of vesicularity, and regions of growth for longer wavelengths of vesicularity. So I like this little schematic over here where you can think, all right, below this 0 point, magma compaction is really beating gas expansion on, say, this little circle, and that's getting squashed away. And then in this region where the red curve is positive, the bubble is actually, the wave of bubble, the bubble and its friends are doing well to push out on the magma so that compaction doesn't beat the wave and compress it away. And so this linear stability analysis was done for a 5-kilometer column in a constant viscosity magma with no exsolution. And what they found for a range of parameters is they found dominant pulses of gas from 10 to 2,000 meters. So when redimensionalized and thought about, the Michaud 2013 model predicts 1 to 100 hours between these gas arrival pulses. And the observed is 3 to 30. So, you know, the linear theory does okay, but that window could be tightened up a little bit. And so I started thinking, how might, you know, making the model a little more realistic affect this idea of a porosity wave filter? Again, I'm calling it a filter because these longer wavelength gas waves seem to break through, whereas shorter features are filtered away or swallowed up during transport up the column. And so, yeah, the simple model doesn't include a model for volatile exsolution from the magma, and then none of the resultant changes in magma properties due to volatile exsolutions. And the stability analysis itself might not tell the whole story because the stability analysis by its very nature assumes an infinite domain and constant conduit properties. And then sort of a secondary goal that was always there is I wanted to push forward the two-phase flow theory so we could come up with more realistic time-dependent multi-phase flow models to apply to magma conduits or volcanic conduits. And so the sort of these goals, these twofold, are sort of tied into this article that, as Joe mentioned, came out quite recently. So I'm going to sort of be trying to give a little summary of this paper and plug it just a little bit. So here's sort of my concept for the time-dependent theoretical model that I'm going to share the results of with you today. So at the base, there is a region that accounts for heterogeneous magma recharge. So this could be feeder dikes from depth going down deeper, but I'm really starting my focus at a shallow magma chamber that sits about 5 kilometers deep in the case of a volcano like Soufriere Hills. This magma chamber can be mixing, convecting. There is a bubble accumulation zone near the top of the magma chamber, perhaps. And at the base here is where I start considering the bottom of my conduit. So the base of the conduit where it meets the magma chamber. So magma may enter the conduit at some injection velocity W. And, for starters, I'm thinking of there being some sort of, magma chamber porosity and magma chamber gas density and magma chamber water content that is sort of forced into the conduit. And so as the magma and gas ascend in the conduit, the water exsolution and gas depressurization ensues. And so bubbles can grow and new bubbles can be formed and potentially form the magmatic porosity waves that I described earlier. And upon reaching the surface, cause the ground deformation that we see on the tilt meter and the periodic dome building and eruptive precursors that are recorded in the seismic and degassing observations. So in order to achieve those conceptual goals here, where I have gas depressurization, some volatile exsolution upon ascent, and thinking about the magma properties, I'm going to need some considerations here, some model considerations. So I'm going to start with the ideal gas law for gas density, so I can linear relate gas density to gas pressure. So for an isothermal magma, this is just a linear relationship between gas pressure and gas density. As I said, I'm using a simple model for magma viscosity, where there's essentially a consideration from the liquid portion of the magma and the crystal portion of the magma. First, the crystal portion of the magma depends how many crystals are in suspension and what the maximum packing fraction of those crystals are. So rigid crystals floating in the melt makes the magma as a whole more viscous. And then here I'm saying I have a sort of constant degassed viscosity for a liquid portion of the magma, and it can be multiplied by some factor that actually discounts the strength of magma based on the amount of water that's dissolved in the liquid. And then lastly, I have to have a model for the magma and the gas in disequilibrium. And so here I've selected a simple model in which the equilibrium dissolved volatile or water fraction dissolved in the liquid is related to gas pressure by a saturation constant. So at equilibrium, this term in the parentheses here goes to 0, and gamma, mass fraction, goes to 0. Now, TR is going to be very important throughout the rest of my presentation. TR is the characteristic exsolution timescale for the water to get out of the magma and into the bubbles. Now, I know that some of these rules or constitutive equations that I'm using here are a lot simpler than some things that you may use for your specific studies, but I just want to remind you I'm trying to solve some time-dependent model that ends up being quite difficult to deal with when I'm worried about the different rates of change for many different things. And so if I'm just putting this up so I can go through it quickly and have it later if someone wants to talk about it. So I guess if you want to discuss this in more detail later, stand back and stand by. But for now, this is conservation of mass of the magma phase. This is conservation of mass for the compressible gas, conservation of mass for the volatile dissolved in the liquid portion of the magma. This is conservation of momentum for the gas in the bubbles or permeable magma. And then this is the total momentum of the mixture. And then I've got some scaling considerations at the bottom, which again, I'm happy to talk about a little later. So I just showed you a nasty slide full of equations, and I did try to linearize it and solve the dispersion relationship analytically, and it wasn't tractable for me. Maybe it is for some of you, but I couldn't figure it out. So I went a different route, and I decided I was going to take my time-dependent model results and interpret them quantitatively. So this is my last non-color slide here, so bear with me. So just like I showed you in the previous work of Michaud, there was this idea of excess gas fraction. So I have that here too. I'm going to write down porosity in terms of my time-dependent porosity minus a steady state model porosity. And assuming that there's wave-like perturbations to my steady state porosity, I can write this new field down as a Fourier series. And if I can do that, I can write down the power spectra. So which frequencies contain the signal's power? And in English, that really means what wavelength porosity waves have amplitude X or Y at a given time or space in my model domain. And so I'm denoting power pi for a given frequency J. Okay, so I want to show you an example of how I dealt with my model output to get some quantitative way of comparing all of my model results. And so we're going to start by looking at this blue ball. There's a blue ball here, there's one here, and there's one here. And so pretend we're just sitting halfway up the model domain, and we start to allow these porosity waves to float past us, right? So I want to point out that I have put 10 superimposed wave-like perturbations at the bottom boundary, and I'm starting with a simple example where there is no water dissolved in the melt. And so if I run this forward in time a little bit, okay, you can see that my ball bounced up and down at this height here, recording the porosity changes as they come by. Well, at this single horizon, I'm recording a time series at a given height, z bar. Now, here, you can see the red line moving forward with the little blue ball. This vertical line here is a top-down view of this profile. So this porosity here ends up being the color bar scale for this contour plot. So as I move forward in this middle panel, I'm saving all of the model results in time. So I draw at a time series at the single horizon, and I can then figure out what the power spectra is at that horizon. Now, interestingly, I have given this 10 perturbations in porosity, as I told you. They all had equal power or equal amplitude coming in the bottom. So they all had amplitude that would have matched here. So this last axis here, this is frequency space. So time, frequency space. And now what I want you to see is that lower frequency or longer amplitude waves have actually grown between the bottom and the middle of the conduit, whereas these higher frequency or shorter wavelength waves have shrunk from the bottom to the middle of the conduit. And you can see qualitatively that really stuff looks spikier in the signal down here than up here. And so what we're showing is that about halfway up the conduit, we have filtered out some of the short wavelength features. So that's the benefit of sort of plotting these time series in frequency space. But then, you know, I just did that for one line throughout my conduit halfway up, and I plotted just the power spectrum for that one spot. But if I did that everywhere throughout my entire model domain, you know, 0, 20, 40, 60, all the way up throughout my entire numerical domain, I could build a stack of these power spectra where Z here is now my model conduit height in some coordinates. Just for your point of reference, I'm assuming a 5-kilometer conduit. And I highlighted 3 of these frequencies for the rest of the talk that represent porosity waves of different lengths. So the blue, these represent porosity waves that once redimensionalized are about 750 meters long. These orange ones are about 170 meters long, and these gray ones are about 90 meters long. So, but back to the power spectrum here. So these lower frequency or longer waves grow throughout the conduit more readily than the shorter frequency waves that grow. And then at a certain point, the very shortest frequency porosity waves are compacted away throughout the column. So this is just for a simple model with no exsolution. But I want to get back to solving the full model now after I've shown you the sort of considerations I need to quantitatively compare my models across models. And so porosity waves might arise on my boundary coming out of the magma chamber for two reasons. First would be oscillations in gas fraction at the bottom, which was the case in the Michaud model. But the second now could be oscillations in water content at the base of the conduit. And that could be due to magma chamber heterogeneity, episodic recharge, or temperature variations. So I can have two different types of wave excitation in my model. One from just directly changing the gas fraction at the bottom around a steady state value, or second, from changing the water content around an equilibrium value, the steady state value. So this is sort of a lot of results in one slide, so bear with me, but this is a full model stack of power spectra, just like the one I showed you before, for models with different characteristic water exsolution timescales. So that means how fast can the water diffuse from the melt into the bubbles. And I started where the fluctuations on the boundary were generated with gas fraction alone. Okay, so Domkohler number is something that I've used as a descriptor here. And this describes the magma advection time scale versus the water exsolution time scale. And so if Domkohler number is large, that means that really think of the magma ascent velocity W as constant. So that means if Domkohler number is large, that means the exsolution time scale is small. So reactions are fast. Domkohler number small over here means that this number TR, so the time scale characteristic for exsolution from the melt into bubbles, is slow. And so in this first family of models that's most similar to Michaud, oscillations due to changes in gas fraction at the bottom boundary don't really do much. So what happens is the filter predicted by Michaud collapses when there is the consideration of exsolution taken into account here. So you don't really see any difference between the growth rate in these 750 meter waves versus the 100 meter waves. They all basically lie flat. And it doesn't seem to matter too much what the reaction rate is. So what this is saying is that that filter, the conduit, doesn't act as a filter anymore, and whatever signal is put out by the magma chamber just passes through the column and is observed at the surface in the model world. Alternatively, if the bottom boundary excites porosity waves due to different amounts of water dissolved in the magma, then something a little different happens. So first, let's look at this, this plot here, D, with a high Domkohler number. So that means fast reaction. So what essentially happens is this red line is the characteristic diffusion length scale drawn with respect to the bottom. So immediately all of the water is dumped out of the magma into the pore space. There's instantaneous sort of maximum bubble growth really quickly, and then this minor sort of gentle filtering similar to what Michaud predicted ensues. However, as the exsolution timescale gets more and more sluggish, and this characteristic diffusion times length scale gets pushed further and further away from the bottom of the boundary, we see a very, very clear sorting, a very pronounced preference for the growth of long wavelength porosity waves. So what this is showing is that in order for this conduit to act as a filter in the mode of porosity wave due to gas expansion and magma compaction, as originally proposed by Michaud in sort of a two-phase flow framework, you need heterogeneity in the magma chamber essentially to drive the excitation of porosity waves at the bottom. So what's really important is that not only does the exsolution timescale matter, but the mode by which the waves are excited matters as well. So another important thing here is to think about the degassing timescale and its relationship to crystal content. And I've actually left out an important nonlinearity in my model where the crystallization of microlights or some other crystal content during ascent changes exsolution rate. But I want to put that on the back burner for now and just show you a simplified picture of what I think is going on here. So for starters, I reproduce some of the linear dispersion relationship predicted by Michaud and others. That's this black line. And then I compared full model solutions using my model with variable crystal contents. And so as you can see, with increasing crystal content, there are faster growth rates across more waves at more wavelengths. And so I should note that I'm comparing this metric Q, where I took the spatial derivative of the power that I showed you in the previous plots. So I'm essentially taking the slope of my power spectra, and the maximum slope tells me the fastest growing point for a porosity wave at some point in my conduit. So what I've done is I've created a numerical proxy for traditional dispersion relationships that I'm trying to use to describe instantaneous growth. And if you're interested in this, there's derivation and a benchmark solution in my new manuscript. But what I wanted to emphasize here is that this maximum growth rate is very sensitive to crystal content. And moreover, at a given crystal content, it's very sensitive to the reaction timescale. So these black circles represent a model with 30% crystals traveling up the conduit and a reaction timescale similar to a day. But if I make that reaction timescale happen quickly on the minutes, the filter, again, as I showed earlier, collapses. And so just to be clear, this point here corresponds with those 750 meter porosity waves. This right here is the 170 or so. And then this guy down here is the 90 meter porosity wave. So a curious thing that popped out of the analysis here that I was not expecting is that gas wave expansion seems to only be weakly dependent on the magma viscosity, but strongly dependent on the crystal content. And so I thought about it this way, and as the crystal content increases at a constant given dissolved water content in the liquid portion of the magma, it results in slower exsolution by changing the balance of the conservation of mass equation for the volatile dissolved in the liquid phase. And so if we increased crystal content as we flow up the conduit, which I've sort of given an example for, the time and length scales comparable to these magma conduit models, we'd expect time scales of about 50 hours at 3 to 4 megapascal decompression rate an hour. We'd get about maybe up to 10% change in crystallinity during flow. And so really during ascent, you would be biasing towards longer and longer porosity waves the entire time you're decompressing the magma and crystallizing with flow. So I took all of my results and redimensionalized the length scales and frequencies that I've been showing you in dimensionless frequency space, and using a range of ascent rates for sort of intermediate composition volcanoes from the review paper Cassidy and others. I find that my porosity waves with wavelengths of with arrival times predicted to be about 10 hours grow 4 times or so faster than those that would arrive hourly. And with the oscillation of volatile on the bottom boundary and the addition of crystals, that growth is exacerbated and biased even more towards the long wavelength porosity waves. And so things of 10 hours might grow 6 times faster than those grow hourly. And then lastly, I just sort of wanted to conclude by saying I don't necessarily think of the porosity wave type model as being a replacement for the stick slip type model. I think that the delivery of these waves to the base of a crystal rich plug could be one of many processes that's helping bias the periodicity observed at volcanoes like Soufriere Hills to the regular periods that we see. However, I am still, agnostic as to what is going on versus which model is dominating, but rather it does seem that just the intrinsic properties of the magma gas mixture starts to point you towards this wavelength of arrival for 10 hours, given the ascent rates that are measured or calculated for Soufriere Hills. So with that, I'll end with Jimmy Buffett, who apparently used to be the same guy as Borat.
Thanks, Jake. We have time for questions and discussion. Please feel free to use the raise a hand feature, and that will allow you to kind of be listed here in my list of people that I'll call on in order, and then, or you can use the chat if you prefer that mechanism. And while I wait for questions to come up, maybe I'll ask a question, Jake, and at your last slide, the slide before Jimmy Buffett.
Okay.
Had these two models, and I was kind of wondering if you thought a bit about trying to bridge these through implementing pretty large rheological changes, or even implementing sidewall friction. Have you tried this first of all, and is this a major change to the model for you to do that, something like that?
Yeah. So astute viewers might have noticed that I actually left out wall friction in my force balance equations. And I did that because the steady state solutions that I'm doing for this sort of slowly upwelling magma column are so moderate that it actually doesn't affect the force balance that I'm caring about a whole lot. I do think that the interaction between a crystal rich plug and my type of model could yield some interesting results wherein my type of model could sort of act as almost like a damped oscillator of supplying pressure to the bottom of this crystalline rich plug. And reality is probably some gradient between these two end member models. I haven't really thought about, kind of going from sort of viscous flow to a true stiff, elastoplastic type model sitting on top of that. But I do thinking about bridging the gap there could be an interesting course of future study, and would have a lot to do with thinking about interaction between these bubble waves and the walls in a more sophisticated way than I have done here.
Right, right. Yeah, it's it going that big. The whole problem is pretty tricky. I'm sure, but even just looking at wall friction might be kind of interesting to put in your.
Yeah, and because I'm not dealing with magma fragmentation or any massive change in magma velocity within the conduit, um, the wall friction really sort of just mitigates my buoyancy force and the force balance. So it's just kind of a discount factor, but it doesn't change my conclusions one little bit.
Well, thanks, Jake. We have some questions lined up here. So, Chris, why don't you go ahead and unmute yourself and ask a question, Chris Harper.
Hi, yes, can everyone hear me?
Loud and clear.
Great. I just, looking at these porosity waves, these compressional waves, they remind me a lot of sound waves in a similar circumstance. And specifically when you said that viscosity didn't have the effect that you expected, made me think, viscosity also doesn't really affect the speed of sound. I was wondering if some of these parameters had similar, like as you varied them, if they had similar effects on just like looking at a very simple how speed of sound would change in those situations. And then similarly, still thinking about sound, how you get these, standing waves and different pipe geometries that kind of set up like a bases. If, anything similar, changing the geometry gave you kind of like a similar change in that with the porosity wave.
Yeah, thanks for the question. So, yeah, I mean, the porosity wave itself, in some sense, is like a viscous P wave. So it is different in that it's viscous. And to your question, sort of, I think it was about resonance frequencies, right?
Yeah.
Yeah. So one thing I was careful to do is, I told you I had different sinusoidal perturbations. Those were all picked based on the length of the column, and I made sure that the frequencies were all prime numbers so I didn't accidentally get normal modes of growth.
Okay. Yeah, no, that's clever.
So I had sort of tried to work my way around that, but I didn't want to get that far down in the weeds when I was setting up the, high level talk.
Thanks.
So I'm just going to go back and forth between the raise a hand and some of the chat questions. And the next question comes from Paul. And Paul, go ahead and unmute yourself if you want to add any of this. But the model seems to predict fastest growth rate at the longest wavelengths. That would be set by the length of the conduit. What does that predict?
Well, so here, and I'll go back a little bit, see if yeah, it's not really letting me. I'm sorry if I offended any Jimmy Buffett fans. Is anyone a Jimmy Buffett fan?
I don't think anybody will admit it now, probably.
Yeah, after I called them a bunch of frat boys and dad rockers. So here, let's see. Yeah, it's not letting me go back slides. I don't know why, but so what I want to show here is figure F does a nice job of explaining this for me. You'll see eventually that no matter what the wavelength of these porosity waves are, right? So low frequency, again, is the long wavelength porosity waves, and these high frequency are the short ones. You do see that there's this tail off here, and that's because the waves are just physically leaving my model domain. So one thing that my analysis does that the linear stability analysis does not do is I do not predict which waves will grow fastest based on an infinite domain. So if my domain were infinite, I could have this huge array of of waves that are possible that are longer than the conduit. And actually, I'm not doing that. So there is a limit on what the fastest growing waves are here, because actually the physical reason for that is if the wavelength becomes too long, it starts interacting with the top boundary before it has time to grow, and you actually lose gas. So I don't know if that helped answer your question, but this versus the linear stability analysis does sort of put more of an upper bound on the most unstable wavelength and how long it can be.
Right, but thank you for that, and thank you for the talk. But I'm still wondering if the longest wavelength admittable is controlled by the length of the conduit, and we have some idea where the shallow reservoir is. What would that predict for the period of the waves that from this model, and how would that compare to the observations?
Right, I see. So the longest wavelength should be about comparable with half the conduit, right? Because the wavelength is a full cycle of the wave here.
Right. Right.
So I think what that would get you is maybe you could make some guess about how deep the magma chamber was if you wanted to trust these numerical results that much, but I don't really know what that gets you. Again, I think these super long wavelength porosity waves start interacting with the surface pretty quickly. So really, and maybe I could have been a little more clear about this, I think these intermediate wavelength porosity waves grow the fastest, not super, super long, but things that are kilometer scale rather than 5-10 kilometer scale, if that helps you.
Thank you.
All right, why don't we go to Leaf next?
Hey there, nice talk, cool work. Guess first was just maybe a follow up on Paul and Joe's comments a little bit, that I do think that adding the wall friction would help in trying to think about growth rates, because that should contribute to damping of these things. But I guess the other question is more about the density perturbations associated with these porosity waves, and whether you ever get large enough amplitudes to invert the density profile.
No, I never got close to large enough amplitudes to invert the density profile. Part of what I did was I tried the amplitude of my perturbations small, so that my growth rates were only functions of the wavelength of the porosity wave and not the amplitude too. I wanted to be able to sort of compare the growth rates across all sorts of wavelengths. So the answer to your question is on the time and length scales for porosity perturbations of a few percent at the pressures we're looking at, it's not enough to invert.
Cool.
All right, let's go down to the chat. This is probably our last question, I'm guessing. This is from Yoshi. Why do porosity waves in the exclusion-free and exclusion-included model decay in the top 20% of the model domain, the conduit? For example, in figures 6 and 8 of your manuscript.
Yeah, so this is what I was getting at earlier, answering one of the questions. That's the wave physically leaving the top boundary. So that's not that shouldn't be ascribed to like a physical volcanological reason, right? That's not some degassing model or something like that. It's like, no, I had these waves conveyor belting by and they started to leave.
Yeah, sorry, you answered that earlier. But I actually have another question talking about the longest wavelengths that exist. And when you say these super long wavelengths, are you now referring to the vertical distance that the excess high in porosity takes up? Are you only talking about the distance between peaks, or is it somehow both? I'm just trying to understand.
Yeah, so it could be both, right? So if you had, we're using sort of the length of the conduit as a point of comparison right now in this line of questioning, I suppose. And so, you know, if you said the wavelength was comparable with the length of the conduit, there would be a porosity peak and a porosity low that both fit within the conduit, I suppose, is one way of thinking about it. So we're really talking about length scale and interaction between the magma chamber and the surface, and if those waves can exist at long enough length scales for those to interact directly.
Okay, thanks.
Mm-hmm.
And we have one more question from Michael. And should we see systematic changes in vesicularity during the eruption? And do we?
Yeah, so there are well-documented changes in vesicularity during eruption, you know, at Soufriere Hills, for example, where there's oscillations between highly vesiculated tephra and denser tephra, you know, even in the same sort of eruption deposits from 1997. So the porosity wave model does do a pretty decent job of capturing maybe some of the predictions that come from looking at the deposits around some of these volcanoes. So it does predict the undulation and vesicularity for similarly composed magmas, I'd say.
All right. Well, thank you very much, Jake. That was great. And again, please look out for Jake's paper that can be accessed. And I'll also post a copy to our website too, or link at least. Yeah, I think I'll leave the line open if you have further questions for Jake, and if he has a few minutes, I'll just leave this line open, and we can have a less formal chat, you know, like talking to people at the podium after the talk. But otherwise, please join us again next week. So next week we have a talk from Fabian Albino. He's going to talk about some really interesting INSAR results and how that relates to dynamics of volcanoes. All right, thanks everybody.